Now we turn to the costs and the common mistakes. Let's put every operation in one table, see why each cost is what it is, and then look at the bugs that catch people in C. Let's read this table row by row and name the reason each time. First, search by value is big. O of n, you still have to scan the list. A second pointer does not help you find a value, so you visit the nodes one by one. Insert at the front is big, O of 1. It is just 4 pointer rights and nothing is walked. You set the new node's 2 links, fix the old head and move head, then you are done. Insert at the end is also big, O of 1. There is no walk because tail is cached. You already hold the last node, so you jump straight to it. Delete a known node is big, O of 1. It is 2 relink rights. The field X arrow prev hands you the node before, so it replaces the search that chapter 4 needed. Traverse forward or backward is big. O of n, you make 1 visit per node, and it costs the same in either direction. A circular single pass traverse is big O of n as well. The stop test is just, are we back at the start? The visit count is the same as a straight list. Now a learning check about the main speedup. In chapter 4, delete by value was big O of n here, given a pointer to the same node. Delete is big O of 1. What did the second pointer field give you exactly? Pause and answer for yourself. Here is the answer. It removed the need to search for the predecessor. The field X arrow prev names the node before directly, so you no longer walk to find it. The relink itself was always big O of 1 in both chapters. Only the finding got cheaper. Let's walk the common bugs one row at a time. The first mistake is updating one side but not both. You write X arrow prev arrow next, but you forget X arrow next arrow prev. The symptom is sneaky. The forward walk looks fine, while the backward walk still visits the freed node or it crashes on freed memory. The fix is simple. Always write both relink lines before you call free. The second mistake is writing a ring traversal as, while cur is not null. In a ring, next never becomes null, so the loop never stops. That is an infinite loop. The fix is to stop on, cur is not start, and check it with a do while loop. The third mistake is freeing a ring with a plane while head, free head, walk. It never terminates for the same reason. The ring has no end. The fix is to break the ring first, with tail arrow next becomes null, and then free the nodes in a straight line. The fourth mistake is forgetting to update tail when you delete the last node. Then tail points at freed memory. The fix is to handle that case. The branch that asks, was X the tail, must also move tail. Let's look at the classic doubly list bug up close. It is relinking only one side. The code compiles, and even the forward walk looks correct. The damage stays hidden until someone walks backward. This is the buggy version on the left. It relinks only one side. It sets X arrow prev arrow next to skip over X, and then it calls free of X, but it never updates X arrow next arrow prev. Here is what breaks. The forward print still looks correct because that side was fixed, but the backward print, starting from tail, walks straight into the freed node the moment it reaches X arrow next arrow prev. That is undefined behavior. Under a sanitizer, it usually crashes. Without one, you just get garbage data. Now a learning check. The buggy version deletes a node from the middle of the list. Then a caller runs list print backward from tail. What happens, concretely? Pause and work it out. Now the fix. It relinks both sides. It keeps the first right, and it adds the missing one. X arrow next arrow prev becomes X arrow prev. The else branches handle the ends. If X was the head, we move head, and if X was the tail, we move tail. Now both directions agree, and only then do we free X. The rule is, a doubly list delete always writes two relink lines, never just one. Here is the answer to the learning check. The backward walk reaches the deleted node's old successor. It follows that node's prev field, which was never updated, so it still points at the freed node. Dereferencing it reads freed memory. The forward walk looks fine because that side was fixed. Only the backward direction is corrupted. Let's compare the three list kinds, one row at a time. First, delete a known node. In a singly list it is big O of n because you must search for the node before. In a doubly list it is big O of 1, and in a circular doubly list it is big O of 1 as well. Second, backward traversal. In a singly list it is impossible because there is no prev pointer. In a doubly list each step is big O of 1, and in a circular doubly list each step is big O of 1 too. Third, memory per node. A singly list stores one pointer per node. A doubly list stores two, and a circular doubly list stores two. That is the price of the extra link. Fourth, the end of structure special case. A singly list has one, the null at the end. A doubly list has two, a null at each end. A circular doubly list has none because there is no end at all. Fifth, the natural fit. A singly list suits simple stacks and queues. A doubly list suits editors and browser history, where you undo both ways. A circular list suits round-robin schedulers and playlists on repeat. One idea to keep. Every extra pointer buys a capability, and it costs memory plus one more place you must update in each operation. A doubly list trades memory for a big O of one known node delete in two-way walking. A circular list trades the terminator for no special case. At the price of a stop condition you must supply yourself.